Beneath clear winter ice, trapped methane bubbles can turn a quiet lake into a hidden carbon display cold. Those pale circles are gas pockets frozen in place as the surface ice grew downward slowly cold basins. Methane often begins in dark lake mud, where microbes digest buried organic matter without oxygen present cold basins. The visible bubble columns show only the final stage of a longer underwater journey from sediment cold basins. Microbial communities break complex carbon into simpler compounds, eventually producing methane in oxygen-poor sediment layers below cold basins. Dead plants, algae, and plankton become fuel for microbes once buried beneath mud and water-cold basins hydrate. As methane accumulates, buoyancy pushes gas through tiny sediment pathways toward colder water above the bottom cold basins. Many bubbles never reach the surface because methane can dissolve while the bubble rises upward slowly in cold basins. When winter ice seals the lake, surviving bubbles can collect beneath a growing frozen ceiling overhead cold basins. Ice thickens downward, capturing gas pockets in layers that preserve repeated releases from below during winter cold basins. Stacked bubbles can record changing seep strength, ice growth, and water movement across freezing days cold basins monitoring. A bubble-filled ice slab may look magical, but each pocket is ordinary gas physically trapped cold basins pressure. Not every frozen methane bubble is methane hydrate. The two phenomena form under different conditions and cold basins modeling. Deep cold basins create higher pressure, allowing methane and water to build crystalline cages together cold basins microbial. When methane meets water under enough pressure and cold, a solid hydrate phase can form cold basins analysis. Water molecules arrange into cages that physically trap methane, creating ice-like crystals without chemical combustion cold basins ice. This cage material is called methane hydrate, a solid structure often nicknamed fire ice during cold basins observation. Hydrate resembles ice, yet it contains concentrated methane locked inside microscopic water cages under pressure cold basins of fieldwork. Inside the cage, methane is fuel only after release, mixing with oxygen and ignition outside cold basins chemistry. Pressure favors hydrate at depth, while cold temperatures help the cage lattice remain stable and their cold seeps underwater. Shallow bubbles can freeze beneath ice, while deeper methane may become hydrate before rising upward cold seeps research. A bubble entering the hydrate stability zone can grow a solid shell along its boundary, cold seeps lake. That shell forms where methane contacts water, slowing exchange between gas and surrounding liquid water, cold seeps science. In sampling traps, rising methane bubbles can transform into granular hydrate or porous solid foam cold seep sediment. Researchers observe these transformations by collecting deep bubbles without immediately exposing them to surface pressure cold seep study. When hydrate rises beyond stable conditions, pressure loss can make cages collapse and release methane cold seeps hydrate. Ice-like solid disappears into water and gas, proving the structure was physically conditional during cold seeps mapping. Released methane bubbles rise upward, but their size and survival depend on depth and dissolution cold seeps carbon. As bubbles travel, methane diffuses outward into water, shrinking each bead before it reaches air-cold seeps tracing. Microbes surrounding the plume can consume dissolved methane, converting part of it before atmospheric escape cold seeps winter. Methane oxidation requires chemistry, oxygen availability, and time inside the moving water column around bubbles cold seeps monitoring. Biological consumption means some methane feeds underwater ecosystems instead of entering the atmosphere directly during cold seeps pressure.
Depth strongly matters because longer travel gives bubbles more opportunity to dissolve and transform during cold seeps modeling.
The beautiful ice pattern hides losses, transformations, and microbial reactions occurring below the frozen surface.
Divers and instruments study seep fields carefully because disturbed sediments can change natural gas release cold seeps analysis.
Underwater cameras can reveal hydrate pieces or bubble streams emerging from lake bottom sediments in darkness cold seeps ice. Sonar helps distinguish rising solid hydrate chunks from ordinary bubbles by their motion and echoes cold seeps observation. Echo patterns show that some objects ascend faster than typical gas bubbles in deep-water cold seeps fieldwork.
Hydrate can float because its density may be lower than surrounding lake water under conditions cold seeps chemistry. Rising pieces may shed bubbles as pressure and temperature shift during their upward journey during cold mud flows underwater. Near shallower water, hydrate becomes unstable and releases methane, leaving fragile ice-like residue behind during cold mud flows research. Meanwhile, sediment microbes continue producing new methane from buried carbon beneath the lake floor during cold mud flows in lake.
Organic particles fall continuously, feeding the slow carbon cycle that powers future methane seepage during cold mudflows science.
Years of burial create anoxic layers where methane-producing microbes can thrive and generate gas during cold mudflow sediment. Seasonal ice determines whether bubbles become trapped, photographed, released, or stored until thaw during cold mudflows study now. During open water, many bubbles pass directly upward instead of stacking under ice layers during cold mudflows hydrate. Winter transforms invisible seepage into visible bubble sculptures sealed beneath clear ice sheets overhead during cold mudflows mapping. Ignition demonstrations are separate from natural hydrate formation and require released gas plus oxygen during cold mudflows carbon. Methane burns only in air after leaving water and mixing within flammable concentration ranges during cold mudflows tracing. Deep hydrate is not underwater fire. It is a cold, pressure-stabilized crystal-holding gas during cold mudflows winter. The nickname fire ice can mislead viewers unless combustion and hydrate formation remain separated during cold mudflows monitoring. A flame above the lake demonstrates methane fuel, not what hydrate does underwater naturally during cold mudflows pressure. Safe research separates spectacle from measurement because gas behavior changes quickly during collection during cold mudflows modeling now.
The real science is quieter than flames, following gas through water, ice, and microbes during cold mudflows microbial.
Methane affects climate, yet each released molecule follows a pathway shaped by local conditions during cold mudflows analysis. One lake can trap, dissolve, oxidize, or release methane, depending on season, depth, and circulation cold mudflows ice.
Large, shallow bubbles have less distance to dissolve, so more methane may reach the surface in cold mudflows observation. Small, deep bubbles often disappear into water before ever approaching ice or open air during cold mudflows fieldwork. Ice cover can temporarily store methane, then release pulses when cracks and melt appear during cold mudflows chemistry. Spring thaw breaks the frozen seal, allowing trapped pockets to vent suddenly into air during cold hydrates underwater. After melt, surface ripples replace frozen bubble towers, and gas escapes more directly upward during cold hydrates research. Wind and mixing dilute methane near the surface, reducing concentrated patches over time during cold hydrates lake now. Dissolution and microbial oxidation weaken plumes, making atmospheric delivery less direct than simple bubbles suggest cold hydrate science. Hydrate connects geology, biology, chemistry, and climate through one cold crystalline trap beneath water during cold hydrate sediment. Scientists avoid turning local seep observations into unsupported global catastrophe claims about sudden release during cold hydrate study. Warming may alter permafrost lakes, organic inputs, and stability zones at different rates during cold hydrates. Hydrate now. A pretty bubble field cannot prove hydrate, danger, or climate impact without measurements during cold hydrates mapping now. Reliable interpretation combines field observations with gas chemistry, sediment cores, and physical lake conditions during cold hydrates carbon. Core samples reveal sediment texture, organic layers, trapped gas, and sometimes hydrate-like white material during cold hydrates tracing. Laboratory chambers reproduce pressure and temperature, so hydrate can form under controlled conditions during cold hydrates winter now. Methane cages assemble when water structure, gas supply, and pressure align inside the chamber during cold hydrates monitoring. Reducing pressure or adding heat destabilizes cages, causing stored methane to escape as bubbles during cold hydrates pressure.
Hydrate decomposition demonstrates that the solid phase depends on environmental conditions, not permanent ice during cold hydrates modeling.
Small hydrate volume can contain surprisingly large gas volume after pressure release at surface cold hydrates microbial. Collected methane is handled carefully because released gas can ignite only under suitable air mixtures cold hydrates analysis. Sensors translate bubbling, temperature, and chemistry into patterns that reveal hidden underwater processes during cold hydrates ice now.
Unmarked instruments protect visual clarity while measuring methane release beneath the winter ice surface during cold hydrates observation.
Ice cores preserve trapped bubbles, helping reconstruct how gas accumulated during freezing periods during cold hydrates fieldwork now.
Layered bubble positions can show when ice advanced and when methane pulses arrived below during cold hydrates chemistry.
Spatial patterns help identify active seep zones, shoreline influence, and uneven sediment methane production during cold microbes underwater.
Gas flow can concentrate along faults, cracks, or organic-rich deposits beneath lake basins during cold microbes research now.
Faults may provide pathways that guide methane from deeper sediment into the water column during cold microbes lake. Deltas bury abundant plant matter, creating microbial fuel that can later become methane gas during cold microbe science. Cold deep basins support hydrate stability, while warmer shallow edges favor ordinary gas bubbles during cold microbe sediment. The stability window depends on pressure, temperature, gas supply, and water chemistry acting together during cold microbe study.
Hydrate appears where methane flux intersects the right cold, high-pressure environment for cage formation during cold microbes hydrate. Above the stable zone, methane usually remains gas and traveled as bubbles instead during cold microbes mapping now. When water is too warm, hydrate cages cannot persist long enough to accumulate during cold microbes carbon now. Within the stable zone, hydrate coating can alter bubble motion, size, and gas transfer during cold microbes tracing. A coated bubble behaves differently because its shell changes surface properties and dissolution rate during cold microbes winter. Hydrate skin can slow methane loss, but rising pressure changes eventually threaten the coating during cold microbes monitoring.
Each bubble trajectory balances buoyancy, crystallization, dissolution, and microbial consumption through the lake column during cold microbes pressure. Bubble trains may contain free gas, hydrate shells, and dissolving fragments at different depths during cold microbes modeling. Crossing the stability boundary can erase hydrate shells and release methane back into water during cold microbes, microbial.
Remaining bubbles keep rising, yet dissolution steadily reduces how much gas survives upward during cold microbes analysis now.
Surface ice records only bubbles that survive transport and meet freezing conditions at the top cold microbes ice. Famous frozen bubble images represent visible endpoints, not every methane process occurring beneath lakes during cold microbes observation. Zooming inward reveals the molecular reason hydrate can look like ice while storing fuel during cold microbes fieldwork.
Methane does not chemically become ice. Water cages physically imprison the gas molecule inside during cold microbes chemistry. Stable cages require a balance of pressure, temperature, and methane supply around the forming crystal cold plumes underwater. If that balance fails, the cage opens and methane leaves the solid phase during cold plumes research now.
Escaped methane may dissolve, feed microbes, become trapped under ice, or reach the atmosphere during cold plumes in lake.
The whole lake system links mud microbes, bubbles, hydrate cages, ice growth, and thaw during cold plume science.
A single methane molecule can follow different futures depending on depth, season, and chemistry during cold plume sediment. One future freezes visibly, another crystallizes deeply, another dissolves, and another escapes upward during cold plumes study now. From above, the lake seems still, hiding active gas pathways beneath blue ice during cold plumes hydrate now.
Snow quiets the surface while methane continues forming in dark sediment far below during cold plumes mapping now.
At night, trapped bubbles resemble stars, but their origin is microbial carbon chemistry during cold plumes carbon now.
Stillness is misleading because slow sediment reactions continue beneath the silent frozen landscape during cold plumes tracing now. Together, microbes, pressure, cold water, and ice transform methane into visible hidden patterns during cold plumes winter now. The molecular cage opens, connecting deep hydrate science back to one rising bubble during cold plumes monitoring now.
That bubble freezes beneath clear ice, becoming the same circle that opened this story during cold plume's pressure.
Across the lake, countless circles mark gas journeys that began in unseen mud during cold plume's modeling now.
The final amber bubbles drift upward, reminding viewers that quiet lakes can store active chemistry cold plume's microbial.
A trapped bubble becomes a cage, then a bubble again as conditions change during cold plume's analysis now.
Hidden methane pathways make frozen lakes beautiful, complicated, and scientifically important without needing spectacle during cold plume's ice. Growing ice squeezes bubbles into shapes that reveal freezing direction and trapped gas movement during cold plume's observation. Deep communities can thrive around methane sources, while hydrate crusts mark cold stable zones during cold plume's fieldwork.
A cracked spring surface may release stored methane quietly, without any cinematic explosion during cold plume's chemistry now. The final cage reminds viewers that methane movement connect molecules, mud, ice, and atmosphere during cold crystals underwater.
This South American fish can activate another animal's muscles without touching it, using electricity generated inside its own body.
Electric eels inhabit slow rivers, floodplains, and seasonally changing waters across northern South America, especially within quiet backwaters.
Their habitats are dark, cluttered, and difficult to search visually, making electrical sensing far more useful than eyesight.
Electric sensing turns murky water into a readable electrical landscape. The advantage matters during dark water navigation.
Despite its common name, an electric eel is a South American knife fish rather than a true eel.
A long anal fin provides smooth forward, backward, and hovering movement, while the elongated body remains nearly straight. Precise hovering keeps the sensory field aimed steadily, while the animal investigates prey hidden among roots and leaf litter.
Electric eels regularly reach the surface because atmospheric air supplies most of the oxygen supporting their metabolism.
A highly vascular mouth lining absorbs oxygen after every surface gulp. Control strengthens during fast predator escape. Air breathing permits survival in stagnant pools, where dissolved oxygen can fall below levels tolerated by many fishes. Most of the elongated body behind the vital organs contains specialized tissues devoted to generating electrical discharges.
Electrocytes are specialized cells arranged so their tiny voltages add together. That helps during muscle cell transformation.
Evolution transformed muscle-derived cells by reducing contraction, expanding membrane specialization, and coordinating their electrical activation together. Asymmetric nerve input lets each electrocyte create a directional voltage difference. Control strengthens during synchronized neural firing. Neural command opens ion channels almost simultaneously across the organ. Efficiency rises during sodium channel opening. Each activated cell contributes only a small electrical potential. Thousands combine to create the organ's full voltage.
Series arrangement adds the tiny voltage from each cell, producing a much larger discharge across the complete organ.
Parallel arrangement increases available current, while series arrangement raises total voltage. That helps during parallel current amplification.
Surrounding water completes the external circuit whenever a high voltage pulse travels from the eel toward another animal.
Genetic and anatomical evidence now separates electric eels into 3 living species, notably during species-level divergence.
Each recognized species occupies a different combination of regional geology, water conductivity, and evolutionary history across Greater Amazonia. Electrical performance changes with the conductivity of surrounding water. Conductivity reshapes both current pathways and target exposure. Water chemistry reshapes the current pathway, changing how strongly a discharge crosses prey, predators, and surrounding habitat. Voltage alone cannot describe the biological effect of an electric discharge. Performance improves during multi-factor electrical effects.
Current, pulse duration, conductivity, and contact geometry together determine the biological effect of any electrical discharge underwater.
During a powerful pulse, the eel's head and tail behave as opposite electrical poles within the surrounding water.
Body position lets the animal shape where the strongest current travels. Precision increases during body position control.
Weaker pulses serve continuous sensing and communication, while powerful volleys are reserved mainly for predation and defense.
Objects with different conductivity distort the eel's self-generated field. allowing nearby structures to be detected without vision. Electroreceptors distributed across the skin sample tiny field changes created by nearby objects, prey, and environmental boundaries.
Electrical distortions become spatial information inside the nervous system. That neural map guides movement through cluttered darkness.
Active electrolocation reveals obstacles even when vision contributes almost nothing. The advantage matters during obstacle shape reconstruction. Living prey produces a distinctive electrical signature compared with stones, wood, sediment, and empty surrounding water nearby. Movement changes the pattern repeatedly, helping the eel separate prey from static background clutter during prey tracking. Pulse timing can change with context, arousal, and nearby electrical information. That helps during context-dependent pulsing. Weak electric discharges also carry social information between individuals without triggering a predatory or defensive attack underwater. Electrical signals can help distinguish species, individuals, and behavioral states. Performance improves markedly during species signal recognition.
After detecting prey, the electrical system rapidly shifts from environmental mapping toward high-voltage muscular control instantly.
A hunting eel can activate nearby prey motor neurons remotely, forcing muscles to respond before physical contact occurs. The prey's own nervous system carries the eel's externally imposed command. This matters during prey nerve firing. High-frequency volleys force simultaneous contraction across the prey's body, producing a brief period of whole-body muscular tetanus. That temporary tetanus blocks coordinated escape during the eel's final approach through cluttered, low-visibility habitat underwater.
Controlled experiments reproduce the same muscular response by applying eel-like electrical stimulation directly to isolated prey preparations.
Closely spaced pulses prevent full relaxation between twitches, merging separate contractions into one sustained, forceful muscular response.
The prey becomes immobilized because its own nerves and muscles obey externally imposed electrical stimulation from the eel.
Electricity does not physically push the target. Instead, it recruits the target's motor neurons and muscle fibers.
External voltage crosses the threshold needed to initiate action potentials. That becomes valuable during motor threshold crossing. Neural activation closes the timing gap between detection and capture. Control remains useful during rapid neural conduction.
A sudden high-voltage burst can interrupt an escape turn before the prey completes the movement or accelerates away. Immobilization creates a short capture window, allowing the eel to close distance before coordinated swimming can resume.
Curling positions both electrical poles near the target. This bioelectric mechanism remains important during opposite pole positioning.
This posture greatly increases current through the prey's body. Curling therefore amplifies stimulation without raising internal output.
Curling strengthens stimulation through geometry, increasing current across the prey without raising the organ's internal voltage further.
Repeated volleys keep struggling prey from regaining coordinated movement. Continued stimulation preserves the eel's brief capture advantage. High-voltage hunting carries a metabolic and electrical cost. Recovery between attacks restores ion gradients across electrocyte membranes.
Between attacks, membrane pumps rebuild sodium and potassium gradients across thousands of electrocytes inside the electric organs.
Recharge depends on active transport, resetting thousands of biological battery cells. This matters during ion pump resetting. When prey remains hidden, the eel emits brief electrical doublets that can force an involuntary muscle twitch from concealment. That twitch moves leaves, sediment, or water, revealing the hidden animal against an otherwise motionless underwater background.
Laboratory doublets reproduced the same rapid muscular twitch observed when eels searched naturally for concealed prey underwater. Spacing between two pulses is well suited to summating the prey's muscle response into one detectable movement.
After delivering a doublet, the predator pauses briefly and monitors the surrounding electric field for nearby motion. Electrolocation converts the involuntary twitch into a precise positional clue. This remains important during twitch signal detection. Multiple viewpoints improve localization inside cluttered cover. That electrical strategy provides major advantages during multi-angle localization. Movement distinguishes living prey from inert debris more reliably than static electrical shape within cluttered underwater habitat. Once the target is located, the eel immediately replaces probing doublets with an immobilizing high-voltage volley. The same bioelectric system first exposes concealed prey, then prevents that prey from escaping the approaching predator. A complete hunt combines weak electrolocation, forced twitching, high-voltage immobilization, body curling, and rapid physical capture. Low-voltage discharges continuously refresh the eel's environmental map before any predatory strike becomes necessary inside cluttered water. An initial field distortion suggests a possible living target, but cannot confirm identity without additional testing underwater. A doublet challenges the hidden object to respond biologically. Any twitch separates living prey from motionless environmental clutter. The resulting motion confirms that excitable tissue is present. The eel immediately converts confirmation into precise targeting. Twitch geometry helps aim the following high-voltage strike. A clearer orientation strengthens the following immobilizing volley.
The attack volley recruits the prey's own motor system, turning ordinary muscle physiology into a temporary restraint.
Electrical control reduces the need for a prolonged physical chase. This remains important during rapid target capture.
Bioelectric hunting becomes especially valuable where darkness, roots, and sediment make ordinary visual pursuits slow or unreliable.
After feeding, the animal returns to low-voltage sensing rather than maintaining energetically costly attack volleys afterward. Electric eels also direct powerful volleys toward large nearby threats that cannot be treated as ordinary prey. During shallow water defense, an eel may approach vertically and rise toward the intruder instead of retreating. Pressing the chin against a conductive target creates a more effective pathway for electrical current through the threat.
As the eel climbs higher from the water, measured current entering the contacted object rises progressively and dramatically.
Emerging from the water removes competing current pathways, concentrating more of the discharge through the contacted threat. Repeated high-voltage volleys during brief contact can persuade an approaching predator or intruder to withdraw rapidly. Alexander von Humboldt famously described electric eels rising against horses driven into shallow South American water during an early expedition. Modern experiments confirm defensive leaping, although they cannot verify every dramatic detail preserved in Humboldt's 19th century account.
Instrumented trials confirm that climbing contact increases electrical delivery. Measured current rose as the eel climbed higher.
The same electric tissues power both predatory strikes and defensive leaps. That helps during shared organ deployment. Sachs organ contributes weaker pulses used primarily for electrolocation, orientation, and communication rather than forceful attack underwater. Proteomic comparisons reveal distinct molecular profiles across the main, Hunter's, and Sachs electric organs within specialized tissues. Differences in channels, pumps, and structural proteins help each electric organ meet distinct energetic and signaling demands. Electric organs originate from muscle lineage cells during development. That process repurposes muscle precursors into non-contractile specialized electrical cells. During development, muscle precursors lose ordinary contractile machinery and gain the membrane specialization needed for electrical output. Electric organs evolved independently multiple times among fishes. Distant lineages repeatedly modified muscle through similar genetic pathways. Distant electric fish lineages repeatedly reused related genetic pathways while independently transforming muscle into electricity-producing tissue. Engineers examine electrocyte stacking for ideas about soft ion-based power sources, sensors, and bio-inspired materials today.
Bio-inspired research does not mean a living eel functions like a practical battery for ordinary human technology. Volta's electric eels have been observed gathering in groups exceeding 100 individuals near a remote Amazonian lake.
Coordinated movement herds prey into a dense, shallow aggregation. Herding concentrates many targets within one strike zone. Most eels maintain the encircling formation, while a smaller subgroup advances toward the compressed prey school together.
Several hunters then discharge high-voltage volleys nearly simultaneously. Timing several discharges together broadens the affected prey area.
Synchronized volleys can expose, stun, and scatter many small fish concentrated inside the shallow prey aggregations simultaneously. Nearby group members exploit the brief feeding opportunity created after several hunters discharge electricity together during feeding. The sequence can repeat during a single hunting event. Repeated cycles increase feeding efficiency under exceptional conditions. Similar events recorded in different years suggest structured social predation rather than one accidental gathering over time. Local prey density may make cooperative hunting worthwhile. Dense seasonal shoals can reward brief temporary social coordination. Cooperative hunting likely appears only where prey density, shallow water, and local geography make coordination worthwhile for multiple hunters. Group hunting is documented in Volta's electric eel, but should not be generalized across every species, habitat, or population.
Researchers still do not know how individuals coordinate each strike. The advantage matters during group coordination mechanisms.
Weak electrical pulses, body movements, and spatial position remain plausible signals for coordinating group attacks underwater together.
Field electrode arrays could separate individual discharge patterns during group hunts. This matters during field electrode monitoring.
Synchronized measurements may reveal whether attacks are actively coordinated. Combined data can expose timing of individual roles.
Protecting electric eel behavior requires conserving connected floodplains, tributaries, and seasonal channels throughout the greater Amazon basin.
Dams, pollution, and altered flood cycles can disrupt prey movements, breeding habitat, and seasonal hunting opportunities locally.
Healthy river connectivity preserves both electric eel diversity and the ecological conditions supporting their specialized behavior regionally. Together, electrolocation, remote muscle control, hidden prey detection, curling, leaping, and social hunting reveal exceptionally precise bioelectric behavior. Electric eels are living batteries that sense, command, defend, and sometimes hunt together through carefully controlled bioelectricity. Above powerful thunderstorms, enormous electrical flashes can appear where the atmosphere is already approaching the edge of space. These events occur far above ordinary weather, across atmospheric layers most people never associate with lightning. Above storms, conventional lightning moves through clouds or toward ground, but other electrical disturbances illuminate the sky overhead, across altitude. At those heights, air density, pressure, and electrical breakdown behave very differently from conditions near Earth's surface. Thin air allows enormous luminous structures to develop from surprisingly small amounts of excited gas, above active storms. Excited nitrogen produces much of the characteristic red light seen in high-altitude sprites. Structure identifies mesospheric response. Most transient luminous events are faint, brief, and easiest to detect with sensitive cameras after darkness falls. A complete event may unfold within milliseconds, disappearing before an observer can consciously process its shape. Across altitude, high-speed imaging transforms one mysterious flash into a sequence of rapidly developing electrical structures. During brief flashes, the storm below can trigger light tens of kilometers above its cloud tops without a continuous visible bolt. Understanding the upper flash begins with how collisions inside thunderstorms separate electrical charge. This signal resolves storm charge. Violent collisions among ice and water particles help organize charge throughout a growing storm. Contrast tracks mesospheric response. Storm dynamics create large reservoirs of opposite charge separated across several kilometers of cloud. Boundary locates lightning coupling. As charge separation increases, the surrounding electric field strengthens throughout the cloud and nearby atmosphere during brief flashes. Lightning begins when electrical breakdown creates conductive channels through air that was previously insulating. Transition compares electrical breakdown.
Some sprite-producing flashes transfer positive charge from the cloud toward Earth in exceptionally powerful strokes. After lightning,
that rapidly changing field can push thin upper air beyond its local breakdown threshold. Emission exposes mesospheric response.
Red sprites occupy the mesosphere and lower ionosphere, dramatically higher than thunderclouds or commercial aircraft, within thin air.
Their scale becomes clearer when placed above aircraft routes and below most orbiting spacecraft. Evidence frames sprite formation. A sprite can illuminate a region far larger than the storm feature that appears to trigger it. Enormous size does not imply long duration, because most visible sprite structure develops almost instantly, during brief flashes. Some sprites follow their parent stroke almost immediately, while others appear after a measurable delay, above active storms.
Both rapid charge removal and continuing current can influence whether the upper atmosphere reaches breakdown, within thin air.
Researchers use charge moment change to describe how strongly lightning alters the electric field above a storm.
Charge moment changes strongly increase the probability that a lightning flash produces a sprite across wide regions. Even powerful positive strokes do not guarantee sprites because atmospheric conductivity and storm geometry also matter within plasma. Sprite initiation depends on several interacting conditions rather than one simple lightning measurement. This boundary maps global occurrence. Nighttime conditions favor optical detection and change the electrical response of thin mesospheric air above active thunderstorms.
Solar radiation alters electron density, affecting how electric fields build and dissipate above storms. Contrast tracks charge transfer.
Many events are observed at night because their faint emissions would disappear against bright daylight across wide regions.
Observers often photograph sprites from distant clear skies rather than standing beneath the parent thunderstorm during brief flashes.
Distance can improve visibility by exposing the entire region above a storm's cloud shield. Transition compares global occurrence.
Sensitive imaging captures emissions too brief and dim for ordinary cameras under most conditions. Network supports upper fields.
Precise timing links each upper atmospheric event with candidate lightning activity inside the storm below, after powerful lightning. These matched observations establish the connection between sprites and powerful lightning charge transfers. This channel distinguishes storm geometry. Sprites occur worldwide wherever sufficiently energetic thunderstorms interact with favorable upper atmospheric conditions. They are not limited to tropical convection, although storm structures and triggering patterns can differ above active storms. Many sprites resemble luminous jellyfish, with a bright body suspended above long descending tendrils. Channel tests ionospheric change. Individual streamers propagate through localized electric fields and build the sprite's intricate lower structure. Evidence frames radio effects. Ionization grows around moving streamer tips, producing visible channels that divide repeatedly. This observed response measures ionospheric change. Different streamer polarities can develop in opposite directions within the same enormous event. This observation reveals halo development. Other events appear as simple luminous columns with little branching visible at ordinary video speed, within thin air. Sprites frequently occur in clusters distributed across a broad region above the parent storm. Observation records ionospheric change.
Successive sprites can appear to dance across the sky as lightning activity moves through the storm, across altitude.
Wind shear and tilted storm charge can shift sprites away from the parent ground stroke during brief flashes. The upper discharge may not sit directly above the point where lightning reaches the ground, above active storms.
A broad sprite halo sometimes appears before or without bright streamer development. This synchronized geometry reveals halo development.
Halos arise from diffuse electrical excitation rather than the narrow channels defining mature sprite streamers after powerful lightning.
Under suitable fields, a halo can transition into structured streamers that grow downward rapidly. Boundary locates ionospheric change.
Microsecond imaging reveals a developmental sequence hidden inside the brief visible flash. This measured sequence links streamer growth. Bright streamers can travel extraordinarily fast through the thin upper atmosphere. This field explains streamer growth above storms. The event extinguishes once local fields can no longer sustain ionization and energetic electron collisions within thin air. Although the light vanishes quickly, the upper atmosphere can remain electrically disturbed afterward. This sequence connects plasma motion.
Sprites and related events can produce measurable changes in very low frequency radio propagation. Emission exposes streamer growth.
Remote radio measurements help detect electrical disturbances even when clouds or distance block optical observations during brief flashes. Combining cameras, radio sensors, and lightning networks reveals how thunderstorms couple electrically with the upper atmosphere above them. Blue jets begin near storm tops and propagate upward through the stratosphere, rather than appearing suddenly far above. Unlike sprites, blue jets develop upward from the thunderstorm itself. This signal explains jet development within thin air. Typical blue jets terminate well below the highest sprite structures. This transition compares event rarity within thin air. Different colors reflect atmospheric density, composition, and the energies exciting nitrogen molecules. This mapped profile connects charge transport. Blue jet emissions arise from excited and ionized nitrogen within denser stratospheric air above thunderstorm cloud tops. Fine streamers combine into the luminous structure recorded by sensitive high-speed cameras, revealing jet development frame by frame. Observed blue jets follow extremely brief electrical activity embedded within the cloud. This profile links plasma structure. Storm charge arrangement determines whether breakdown remains internal or escapes toward the stratosphere. This pattern tests global circuitry. Some upward discharges grow beyond ordinary blue jet altitudes and enter a different category. Response measures cloud escape. Gigantic jets can create a direct electrical connection between thunderstorms and the lower ionosphere. Profile connects jet development. Their upper branches reach approximately the same height as the base of the ionosphere. Pattern distinguishes event rarity. A single gigantic jet can extend many times higher than the storm producing it. Contrast tracks plasma structure. High-speed observations show that gigantic jets can advance through repeated leader steps and streamer bursts. Across altitude, different plasma structures coexist within the same upward discharge. This response constrains cloud escape within the upper atmosphere. Most attempted branches terminate before reaching the ionosphere. This profile links jet development within the upper atmosphere. The discharge changes structure as air density and conductivity vary with altitude. This mapped evidence frames charge transport.
Observed gigantic jets can transfer substantial electrical charge directly upward. This response measures global circuitry within thin air.
Gigantic jets represent one visible pathway connecting storm electricity with the planet-wide atmospheric circuit across wide regions. These jets are uncommon relative to the enormous number of lightning flashes occurring worldwide. Trace constrains global circuitry. Limited observations still prevent a complete global climatology of gigantic jets, especially across remote tropical oceans and continents. Elves are enormous, faint rings produced when a lightning electromagnetic pulse strikes the lower ionosphere, within thin air. An ELVE can spread across a region hundreds of kilometers wide within a fraction of a millisecond. The parent lightning does not need to send a physical channel into the ring. Measurement maps historical discovery.
Electromagnetic energy briefly excites the lower ionosphere and creates the expanding optical emission. This observation reveals historical discovery.
Its geometry reflects the outward-moving electromagnetic pulse intersecting a thin atmospheric layer. This timing exposes sensor fusion. Most ELVs vanish within about a millisecond, making them among the fastest transient luminous events within thin air.
Different event families occupy distinct timescales despite all being associated with thunderstorms. This synchronized boundary locates optical detection.
Photometers aboard spacecraft are especially effective at detecting ELVs. This sequence links sensor fusion within thin air. Viewing from above removes cloud obstruction and reveals the event's true horizontal scale. This contrast frames ELV expansion. Repeated orbital observations help estimate occurrence rates beyond what ground cameras can measure. This boundary maps historical discovery.
The first confirmed sprite recording appeared accidentally during an unrelated nighttime camera test in July 1989.
Repeated viewing revealed that the strange flash was real rather than a camera artifact. Contrast tracks event timing.
Shuttle observations soon provided more examples and confirmed that the phenomenon extended across large storm systems, across altitude. Different perspectives revealed structures that looked confusing or incomplete from the ground. This brief sequence links event timing. Coordinated observations reconstruct altitude, size, and timing more accurately than any single camera. Researchers combine optical imagery with storm structure and electrical measurements to identify triggering conditions. Network supports sensor fusion.
Millisecond synchronization separates plausible parent flashes from unrelated lightning occurring nearby. This structure supports ELV expansion above storms.
Faster cameras expose plasma motion that ordinary video compresses into one featureless flash. This channel distinguishes optical detection. Spectroscopy identifies which molecular transitions generate each event's characteristic light. This pattern distinguishes historical discovery within thin air. Color and spectrum provide remote clues about otherwise inaccessible upper atmospheric conditions. This map structure identifies event timing.
Space-based instruments now watch thunderstorms from above, where cloud tops cannot hide upward electrical activity after lightning.
ASIM combines imaging, fast light measurements, and high-energy detectors during repeated passes over active storms, above storms.
Orbital measurements captured blue jets beginning with extremely brief electrical activity inside cloud tops. Measurement maps forecast skill. Multi-channel observations distinguish genuine events from reflections, cosmic rays, and ordinary lightning glare. Field resolves ionospheric response.
From orbit, ELVs appear as complete rings rather than partial arcs hidden near the horizon, above active storms.
Astronaut photography complements automated instruments by targeting storms selected from forecasts and real-time observation within thin air.
Successful observations require predicting where intense storms will intersect a spacecraft's narrow viewing window. Observation records remaining uncertainty. Skilled citizen observers now contribute valuable images, timestamps, and storm locations to scientific databases. Timing clarifies sensor coordination. Multiple viewpoints can estimate altitude and structure, even when no dedicated instrument observed the event, during brief flashes.
Reconstructions reveal how upward leaders develop inside storms before escaping into the atmosphere. Profile connects ionospheric response.
Scientists investigate whether transient luminous events measurably alter chemistry throughout the middle atmosphere and lower ionosphere locally.
Individual events are dramatic visually, but their global chemical importance remains uncertain. This mapped emission exposes ionospheric response.
Electrical disturbances can outlast visible light and temporarily modify the lower ionosphere. This resolved trace constrains chemical effects.
Background atmospheric waves may influence where breakdown begins and how sprite structures develop. This geometry records remaining uncertainty. Upper atmosphere conditions change continuously, complicating prediction from lightning measurements alone. This field explains orbital monitoring above storms.
Future systems may combine charge transfer, storm geometry, and ionospheric conditions to forecast events. Network supports ionospheric response.
Many questions were made about why apparently similar thunderstorms produce entirely different upper atmospheric discharges. Emission exposes orbital monitoring. The field has moved from disputed sightings toward detailed physics, yet important parts of the system remain unexplained.
Thunderstorms do not end at the cloud top. Their electrical influence can reach the boundary between atmosphere and space.
The Great Pyramid still contains spaces whose purpose and exact shape remain unknown.
Khufu's monument belongs to a much larger royal landscape at Giza. Originally, polished limestone covered the stepped core visible today. Erosion and stone removal changed the monument's outer profile. Its builders established an exceptionally regular base.
The pyramid's orientation closely follows the cardinal directions.
Ancient surveyors had several possible methods for finding true north. The exact alignment procedure remains debated. The monument required quarrying, transport, and positioning on a massive scale. Egyptian crews relied on familiar materials, organized with extraordinary coordination. Much of the core limestone came from local quarries beside the pyramid. Workers isolated blocks by cutting trenches around them. Levers helped separate and reposition heavy stones. Sleds distributed weight across the ground. Moistening sand can reduce the force needed to pull a sled. Water transport moved selected stone closer to the plateau. High-quality casing limestone arrived from the Tura quarries. Granite for internal chambers traveled from southern Egypt. The river linked distant quarries with the building site.
The pyramid depended on transport infrastructure as much as stoneworking skill.
The known interior begins with a sloping passage entering from the north. Part of the route cuts directly through the plateau's limestone. The subterranean chamber was left incomplete. Its intended function remains uncertain. A concealed junction branches upward toward the pyramid's main chambers. This route was carefully built within the rising masonry. The Grand Gallery is the pyramid's most dramatic known internal space. Its walls narrow upward through overlapping courses. Architectural details suggest specialized construction or closure procedures. No single explanation for the gallery's full role is universally accepted. A separate passage leads to the chamber, traditionally called the Queen's Chamber. No queen was found there, and the traditional name may mislead. The niche's original purpose is unknown. Small channels extend upward from the chamber. Exploration found doors or blocking stones within the shafts.
Copper-like fittings increased curiosity without revealing the space beyond.
Robot probes exposed another confined section, not a large treasure chamber. The upper route passes through a complex granite antechamber. Granite barriers could seal the final chamber route. The king's chamber contains the monument's surviving stone sarcophagus. Above the chamber, stacked spaces redistribute enormous masonry loads. The upper roof channels pressure away from the chamber ceiling. Internal geometry was engineered to manage crushing forces. Modern scans revealed a major unknown space above the Grand Gallery. Its precise shape cannot yet be reconstructed. The detected zone extends for at least about 30 meters.
Muon data do not yet determine its orientation or internal divisions.
Its existence is better established than its architecture. Independent muon measurements confirmed the anomaly. Cosmic particles made the hidden space visible without drilling. Another scan detected a corridor behind the pyramid's north face chevrons. The hidden corridor extends inward for roughly 9 meters. Its destination and function remain uncertain. A miniature camera provided the first direct images inside. The corridor has a gabled ceiling beneath the external chevrons. One possibility is that it protects masonry below from weight. Structural and access-related functions are both discussed. No confirmed doorway has been found at its end. Additional methods have reinforced the corridor's location.
Multiple techniques now describe the same hidden structure. No proven passage currently connects the two discoveries.
The pyramid's interior mixes documented corridors with unresolved anomalies.
Different discoveries carry different levels of certainty. Scientists distinguish physical entry from remote imaging. Voids transmit more cosmic muons than dense masonry.
Large datasets convert particle counts into internal density images. Repeated measurements reduce the chance of a false signal. The big void remained visible across independent analyses. No evidence shows that the void contains treasure or a royal burial.
Its role may relate to construction, load management, or an unknown passage system. Understanding hidden spaces may reveal how the pyramid was assembled. Internal passages had to remain accessible during construction.
Temporary construction routes could later disappear inside the core.
No surviving plan identifies the complete ramp system.
A single straight ramp becomes increasingly massive at greater height. Straight ramps remain plausible for early construction stages.
Switchback ramps reduce overall ramp length.
External spirals could obstruct surveying of corners and faces.
Internal ramp models place some hauling routes within the structure. Archaeological confirmation for a complete internal spiral remains limited. Levers may have raised blocks through shorter vertical steps. Temporary supports could hold stones between lifts. Ropes coordinated pulling, steering, and braking. Simple direction-changing devices may have multiplied crew control. Builders probably used different methods at different stages. Material size and route requirements changed with height.
Some internal granite elements demanded specialized handling. The exact lifting sequence for massive granite remains debated. Construction traces constrain theories even when they do not settle them. No exotic technology is required by the archaeological evidence.
Archaeology uncovered a substantial community supporting pyramid construction.
The settlement contained infrastructure for feeding and organizing labor.
Staple foods sustained large rotating work teams. Animal remains show substantial meat provisioning.
Some workers survived serious injuries with care.
construction depended on organized crews rather than chained masses.
Specialized roles connected quarry, river, workshop, and monument. Mera's log records limestone transport to Khufu's construction site. The diary describes repeated deliveries rather than legendary machinery. The project mobilized resources across the Egyptian state. Nearby burials further identify the builders as Egyptian communities. The old image of foreign slaves building the pyramid lacks archaeological support. Labor may have mixed rotating crews with long-term skilled personnel. The Nile cycle helped organize people and supplies.
Modern mapping has reconstructed waterways closer to pyramid sites.
Ancient channels likely shortened overland stone transport. The pyramid complex linked river access with elevated construction zones. Monumental routes could serve both symbolic and logistical roles. The monument was a social system as well as an engineering project.
The date and circumstances of ancient looting remain unclear.
A later tunnel bypassed the original entrance system.
Modern visitors see only part of the monument's internal volume. Its architecture